Hi everyone, I am Dr. Jafari. Many students told me to prepare a video about theories of beams, and so in this video I'd like to talk about this subject. Generally, one can classify the beams theories into two categories. The first category is classical or Euler-Bernoulli beam theory, sometimes called technical beam theory, and the second one is the shear deformation theories of beams. I have to say that there are several shear deformation theories of beams that have been presented by many researchers, and in this video I'd like to talk about two well-known shear deformation theories of beams, namely first order shear deformation theory, FSDT, which is famous as the Timoshenko beam theory, and the another one that I will talk about is Reddy's third order shear deformation theory, TSDT. You can search in the literature and you will certainly find some other shear deformation theories. Let me talk about the general points in classifying the beam theories. You may know that the bending effect, or one can say the bending moment effect, is a necessary part in the modeling of beams and has significant influence on the beam response, and it will never be ignored. Likewise, the transverse or vertical inertia has to be considered in the dynamic analysis of beams. In other words, the bending effect is necessary for static analysis of beams, and the bending effect and along with the transverse inertia effect are necessary for dynamic and vibration analysis of beams. I should say that there are two other effects that may have significant influences on the beam response. These two effects are the shear effect or shear strain effect or shear stress effect or even shear force effect, and also the rotary inertia effect. It can be shown that for a thin beam, I mean a beam with high slenderness ratio, L over H, the shear and rotary inertia effects are not significant and can be neglected. But for a thick beam, I mean a beam with a small slenderness ratio, the shear and rotary inertia effects are important and cannot be ignored. Let me show this table. In this table, you can understand the differences between some theories of beams, as you can see. In the Euler-Bernoulli beam theory, the shear effect and the rotary inertia effect are ignored, and in other words, only the bending effect and the transverse inertia effect are considered. In the Rayleigh beam theory, only the rotary inertia effect is taken into account, and the shear effect has been ignored. In the shear beam theory, the shear effect is considered, but the rotary inertia influence is ignored. And finally, in the Timoshenko beam theory, both effects, I mean the shear effect and the rotary inertia effect, are considered in the analysis. In the next slides, I will talk about classical or Euler-Bernoulli beam theory, first order shear deformation theory, FSDT, and Reddy's third order shear deformation theory, TSDT. In this slide and in the left figure, the beam's cross-section in an arbitrary position X before loading and deformation is shown. As can be seen, the beam is placed in the XY plane in a right-handed coordinate system. The right figure depicts the beam's cross-section after loading and deformation, and the dashed dotted line signifies the midplane of the beam. You can see the midplane here before deformation and here after deformation. Likewise, U0 of X and T and also V0 of X and T are the displacement components of the midplane in the X and Y directions respectively. The line OA is the tangential line to the deformed midplane, and OB is the line of the cross section, and the partial derivative of V0 with respect to x is the slope of the line OA to the deformed midplane. The classical beam theory is based on some fundamental assumptions, and assumptions is that the line of the cross section OB initially normal or perpendicular to the mid surface remains plane or straight and normal to that surface after bending. It is very important to note that this assumption means that the vertical shear strain epsilon xy is negligible, and this is compatible with ignoring the shear effect that I said and emphasized before. Another assumption is that the stretching and compression of the beam in the thickness-wise direction can be neglected. I mean epsilon y equals 0. The displacement field for the Euler-Bernoulli beam can be written as equation 1. In this equation, u of x, y, z, and t, v of x, y, z, and t, and also w of x, y, z, and t are displacement components of an arbitrary point of the beam in the x, y, and z directions respectively. As you can see from this equation, it is so usual to write the displacement fields based on the displacement components of midplane, that is u0 and v0 in our problem. Let me explain how to write this equation. Imagine a point above the midplane. Imagine a point above the midplane. I mean a point with positive y. If you want to write its displacement in the x direction, for example, you can write it with respect to the midplane. So you say its displacement equals midplane displacement, the first term in the right hand side of first equation. So you can say that its displacement equals midplane displacement plus the relative displacement between that point and midplane, both in the x direction. As can be seen, since the relative displacement is to the left, so the minus of it is considered in the first equation, as you can see. The second term of displacement field, v equals v0, is obtained based on the second assumption shown in the previous slide, in which we say that the stretching and compression of the beam in the thickness-wise direction can be neglected. In other words, epsilon y equals 0. And about the third term of displacement field, w I mean, one can understand that the displacement of the beam in the outward direction, z direction I mean, is neglected. Another simplifying assumption is that the midplane remains unstrained, and so one can assume u0 equals 0. So using this assumption, the final form of displacement field of the beam based on the Euler-Bernoulli beam assumptions can be as equation 2. The general form of the strain displacement relation has been presented in equation 3. In this equation, epsilon x, epsilon y, and epsilon z are the normal strains, and gamma xy, gamma xz, and gamma yz are shear strains. As can be seen, and for instance, epsilon x equals the first partial derivative of u with respect to x. Similar expressions are presented for other strain components. Upon substitution of the displacement field in the well-known strain displacement relation, we have equation 4 for all strain components, As can be seen, only epsilon x is non-zero and other components of strains are zero. As can be seen, the epsilon x equals minus y multiplied by the second derivative of u0. I'm sorry, the second derivative of v0 with respect to x. Also, all three shear strain components are zero, but gamma xy equals zero signifies the ignoring of the shear effect in the Euler-Bernoulli beam theory. It is so important, and so please keep it in mind. The non-zero stress component is sigma x and can be calculated as equation 5, in which E is the elastic or Young modulus. As you can understand, until now, only the bending effect has been considered and the shear effect has been ignored in our analysis. Let me next present the strain potential energy of the beam by considering the linear elastic material. The general form of strain potential energy of a structure can be calculated as equation 6. In this equation, sigma x, sigma y, and sigma z are normal stresses, and tau xy, tau xz, and tau yz are shear stresses. After substituting the equations 4 and 5 in equation 6, we have equation 7. In equation 7, L is the beam's length and A is the area of its cross section. By defining this integral, I mean equation 8, which is the second moment of the area along the z-axis, the final form of the strain and potential energy can be calculated as equation 9. You are familiar with this equation in elementary subjects like the strength of materials. Now let me talk about inertia terms. We can say that the general form of the kinetic energy is as equation 10, in which rho is the density of the beam. Likewise, u dot, v dot, and also w dot are the velocity components of an arbitrary point of the beam. It is clear that dot means derivative with respect to the time, and also v is for the volume. It is clear that the integration should be done through the volume of the beam. Upon substituting the displacement field, I mean equation 2, in the kinetic energy equation 10, we have equation 11 for the kinetic energy of the beam. Using the definition of I, second moment of area, and also A for the area given in equation 12, we have equation 13 for the kinetic energy. We can say that the first term on the right hand side of equation 13 represents the rotary inertia term, and the second term represents the vertical inertia. As I said before, the rotary inertia term is ignored in the classical beam theory, and so the final form of the kinetic energy is as equation 14. Having in hand the final form of kinetic energy, equation 14, and the strain potential energy equation 9, and by calculating the work done by external force and then by applying the Hamilton's principle, one can obtain the governing differential equation for the beam. I have to say that this is not the object of this video, and so I leave it for another time. From this slide, I will talk about the first order shear deformation theory, FSDT, or as I said before, Timoshenko beam theory. You remember that I told in the Timoshenko beam theory, both effects bending effect and shear effect have to be considered together. You can use the superposition principle. A simple statement of the superposition principle is that if there is a linear relation between input and output, so we can apply the inputs one by one and then obtain the corresponding output. And finally, the total output will be the sum of all outputs. This principle is valid for a linear system. It is so important that this principle is only valid for a linear system. In our system, it is clear that there is a linear relation between inputs, I mean bending moment and shear force, and output, I mean beams deformation. So we can use the superposition principle. This figure is for an arbitrary cross-section of the beam in the distance x before deformation, and the dash dotted line is for the midplane. First, we only consider the bending moment, and so this case is similar to that discussed in the Euler-Bernoulli beam theory. M denotes the bending moment of the cross-section. O prime, B prime is the line of the cross-section, and also O prime, A prime is the tangential line to the deformed midplane, and psi is its slope due to the bending moment, so it is called bending rotation. As you can see, the O prime A prime is perpendicular to O prime B prime because we consider only the bending effect as we had in the Euler-Bernoulli beam theory. In this figure, only the shear effect is considered. As before, O double prime B double prime is the line of the cross section, this line I mean, and O double prime A double prime is the tangential line to the deformed midplane, and beta is its slope due to the shear force, so it is called shear angle, and V is the shear force. We will show that the shear angle represents the shear strain, but with minus sign because of the defined coordinate system. Please note that the line O double prime B double prime remains vertical when the cross section is only due to the shear force, as it is shown in this figure. Using the superposition principle, the final deformation of the cross section will be the right figure, this figure I mean. From superposition, it is clear that the lines OA and OB are not perpendicular to each other in this theory. Likewise, the slope of the line OA is psi minus beta, which equals the partial derivative of V0 with respect to x. Similar to the points mentioned in the Euler-Bernoulli beam theory, the displacement field for the Timoshenko beam theory is as equation 15. You can see the displacement field here again. You may ask why Timoshenko beam theory is called first order shear deformation theory FSTT. To answer this question, I prefer to remember you the Taylor series. You know that the Taylor series of a function f of y that is infinitely differentiable at point A is the power series like this equation. F of y equals f evaluated at A plus the first derivative of f evaluated at A over 1 factorial multiplied by y minus a plus the second derivative of f evaluated again at a over 2 factorial times y minus a squared plus the third derivative of f with respect to y evaluated again at a over 3 factorial times y minus a cubed and so forth. We can use the Taylor series to explain to expand the first term of equation 15 like this. As you see, u of x, y, z, and t equals u evaluated at y equals 0, I mean evaluated at midplane, plus the first derivative of u with respect to y evaluated at y equals 0 over 1 factorial multiplied by y minus 0. By comparing this equation and equation 15, it is clear that the first term on the right hand side is replaced by u0, and the second term is replaced by minus y times psi. Please compare this equation and this equation. Since the first order of series in Y is considered in the Timoshenko beam theory, this theory is called the first order shear deformation theory, or FSTT. You can understand that in the third order shear deformation theory until the third term will be considered. By ignoring the u0 in equation 15, we can write the final form of displacement field for the FSTT as presented in equation 16. And if we obtain the strain components using the strain displacement relations presented before, they will be as equation 17, as can be seen. The epsilon x and gamma xy are non-zero strain components, and other strain components are zero. As I said before, the gamma xy is equal to minus beta. Please see here the shear angle, I mean beta, the shear angle. Likewise, I should say that if we assume psi equals the partial derivative of v0 with respect to x, these strain terms and also the displacement field 16 will be reduced to those obtained in the Euler-Bernoulli beam theory. By ignoring the Poisson effect, the non-zero stress components will be the normal stress sigma x and shear stress tau xy, in which G is the shear modulus. I should say that the main critique of the Timoshenko theory is that it predicts the constant value for shear stress and also shear strain in an arbitrary position x, but you may remember from elementary topics in the strengths of materials that, for example, for a rectangular cross-section of the beam, the shear stress distribution will be parabolic. To correct this inconsistency to get better results, for example, for deflection, the shear correction factor will be multiplied like equation 19. It is clear that by multiplying the correction factor Ks, I mean the shear correction factor Ks, it is clear that by multiplying the correction factor, the shear stress and also shear strain distribution isn't corrected, but generally the results will be better. If you want to calculate the strain potential energy, it will be obtained as equation 20. It is clear that the first term in the integral is due to the bending effect, and the second term will be due to the shear effect. Moreover, if you try to obtain the kinetic energy of the Timoshenko beam theory, its final form will be as equation 21, in which the first and second terms represent the rotary inertia and the vertical inertia effects respectively. Last theory we discussed in this video is Reddy third order shear deformation theory, which had been presented by Professor Reddy. As I explained, for the Timoshenko beam theory, using the Taylor series, we can write the displacement field until the third order for u of x, y, z, and t. In the Reddy's third order shear deformation theory, I mean. As you see in equation 22, u of x, y, z, and t equals u0 minus y times psi plus y squared times phi of x and t plus y cubed multiplied by omega of x and t. V and W, V of x, y, z, and t, and also W of x, y, z, and t are the same as before. Using this figure, it is so easy to understand that the transverse shear stress, is zero at the top and bottom of the cross section. You can see here. I mean at y equals h over 2 and also y equals minus h over 2. The shear stress is 0. From the stress-strain relation, we can write equation 24. Upon substituting equation 22 into equation 24, we have equation 25. The results presented in equation 26 can be easily obtained from equation 25, and so the displacement field for this theory can be written as equation 27, as you can see here. This is the final form of displacement field for the third order shear deformation theory. The same as before, we can ignore u0 in equation 27, and so the final equation for the displacement field of this theory can be obtained as equation 28. The strains and also the stress components will be obtained as equation 29 and 30. Respectively. The main point is in the shear strain gamma xy. It is clear that the shear strain is almost given the true distribution, and so in this theory we don't need to use the shear correction factor which had been used in the Timoshenko beam theory. Having in hand the stress and strain components, the strain potential energy can be calculated. Likewise, using the final form of displacement field for TSDT, the equation 28, as you can see here, the kinetic energy can be obtained. I leave the calculation of these energies for you, and I'm sure that using the previous slides it is easy for you to calculate the strain potential and also kinetic energies. Finally, I would like to say some points. First point is that OA and OB are perpendicular to each other in the Euler-Bernoulli beam theory, but they are not perpendicular in the shear deformation theories, which are due to considering the shear effect. The second point is about the shape of line OB after deformation. By referring to displacement fields for different theories discussed in this video, we can say that the line OB remains flat after deformation in the Euler-Bernoulli beam theory and also in the Timoshenko beam theory, but it is clear that after deformation in the third order shear deformation theory, it's not flat and will be a curve. The third point is that TSDT predicts more flexibility for beams than the Timoshenko beam theory, and also the Timoshenko beam theory predicts more flexibility than the Euler-Bernoulli theory. In other words, the overall stiffness of the Euler-Bernoulli beam theory is greater than the Timoshenko theory, and also the overall stiffness of the Timoshenko theory is greater than the TSTT. From this point, from the third point, we can say that deflection of the beam based on the TSTT is the biggest one, and also the frequency predicted by the Euler-Bernoulli is the biggest one. If this video was useful for you, please like it, and also please recommend it. Likewise, please subscribe my channel. I will prepare and upload other videos on this channel in the near future when time permits. Thank you so much for your attention.